Hello and welcome to another video. In this video we're going to be working on minimum number of moves to seat everyone. And in this one you have n seats and n students in a room. And the seats is an array and the students is an array, and the number is just the location. So there you have like a seat at location 2, 2, 6, and 6. Students at 1, 3, 2, and 6. And you want to see each student in a seat, and to move a student takes one move per distance it moves. So if it goes from 2 to 4, it takes 2 moves and so on. You want to minimize the number of moves and get each student in a unique seat. So they kind of show you these examples of what happens, but essentially you can kind of try this out and you're going to realize that, and the best way to do this kind of problem is you don't actually need to get like the exact right thing. In fact, usually what I do sometimes is I make an assumption, and if I can't break it, I just make a solution based on that. And then there'll be just edge cases that will be like, oh yeah, those broke my assumption. So the assumption you can make here after trying this a few times is you actually want to keep the order of the students the same as the seats. So for example, let's say we have 3 seats in green. So let's say we have seat 1, seat 2, seat 3. And we have 3 students. So if the students are like not in between the seats, like if they're like this, let's say, it doesn't really matter where you put them. Like it's all going to be the same thing. And that's because they all take the same, like no matter where you put them, they all have to get here. And then from here, 2 students have to move to here and here. So no matter which ones you pick, it's going to be the same. So the only time it matters is if the seats and the students are between each other. And basically the assumption you can make here, and you can try to break it, and I don't think you can, is if you have some seats and some students, you want to place, let's say this, you want to place the same order of the student as the seat. So student 1 will go here, student 2 will go here, student 3 will go here. And so you can try this out and see if you can break it. But yeah, that's basically what you can realize, and you can go through like more examples of why that is. I don't know if there's like a concrete proof, and usually you don't need to make a concrete proof for these problems. You just need to make an assumption that you think is pretty good and pretty reasonable. And that happens a lot with these problems. Is the really nice optimizations that you're going to make is you're going to make an assumption that seems pretty good. You're going to try to do something that breaks it. And there's not like too many different examples here that can break it. But yeah, essentially, like maybe I'll place the seats, here, and maybe I'll put student 1 over here, student 2 over here, student 3. Well, actually, this is kind of clear as why that's the case. Maybe I'll have something like this. Maybe I'll have like a seat 3, and then I'll have like student 1 over here. Or maybe I'll put them all here or something, try something like that. And so you can kind of tell that here, like I said, these two don't really matter where they go, but this guy is going to be the best person to put here. These two don't matter where they go between these 2 seats because they're both to the left. But like, for example, you're not going to want to do this and this here or something, right? So if you know both of these are going into these 2 seats, it's not going to matter. Like you can do this, which is 1, and this, which is 1, 2, 5, which is 6, or you can do it this way, which is 3, and this way, alright, sorry, this is 4, this is 2, so it doesn't matter. Because like I said, when you have 2 students and you're placing them in seats that are not like intertwined with them, it doesn't matter. But when they all have to move in different directions, it does matter. So in this case, 3 would 1 go here, and then these 2 you can do whatever. But essentially, if you just do the operation of 1 goes in 1, 2 goes in 2, 3 goes in 3, that's always going to be your best. So now that you know that, what's going to be like the way to solve this problem. So now it's pretty easy. So we can just sort our seats and we can sort our students, and then we know that like the same index has to match, and then we can just see like what's the distance there. So for example, if we have these seats 2, 2, we can sort our seats, we can sort our students, and then we know like this student needs to go in this seat, this needs to go here, and so on. So you can just do the difference, and that will give you 4. And you can do that for all of them. So that's essentially all we need to do for the problem. I do think it's maybe a little tougher than an easy problem to realize that. Like I don't think it's the most intuitive thing to realize that like the order of the students has to match the seats. But like I said, just try a few examples. First, try like all the students on one side. Like just try a bunch of different edge cases. Try to see if there's a pattern. If there's not, then you're probably gonna need a more complicated algorithm like DP or some other, because then you have a decision, right? For every student, like where do I put them? Things like that. That might give you a decision, and that might be like DP. But in this case, there's like a greedy optimization where we could just say the indices need to match. So that's what we will code. So let's do that. So we'll sort our seats. we will sort our students. And then we can just loop. And yeah, I think you can probably come up with like a more accurate proof if you want to. Just go through like 3 seats and 3 students and try to get like all possible variations and see why they all work. And that would give you like a better, probably something better. But I just basically that's the first thing I thought of, and I was like, can I break it? And I tried different things, and it was never worse, so it worked out. So here we have plus. Then we just get a difference. So seed psi, and we want absolute value minus students. Okay, and just return. Oops, there we go. And yeah, so the actual coding is easy, but the figuring it out is the hard part. And like I said, this is very common where you have some operation you get to play around with. So the best thing to do is just play around with it, try a bunch of different things, see what you can come up with, see what optimizations you can come up with. Because for the most part, for harder problems, you will have these things and you will have to come up with an optimization. Like you won't just do the brute force, you know, just like try everything. Like there is some trick usually in the operation that you're doing that you can use to optimize it. So in this case, this is going to be O of log. They're the same length, so it's n log n to sort both. And then to go through it, just O of n, and space is 0. So yeah, it's going to be all for this one. Hopefully you liked it, and hopefully you do get used to these problems. This is kind of like a warm-up to, you know, doing these operation problems. And this is more just like, there isn't like really an algorithm to study for this. It's more just like, can you get something you can do, and can you come up with intuitively some kind of like shortcut to getting what you want. So hopefully it was helpful. If it was, please like the video and subscribe to the channel. And I'll see you in the next one. Thanks for watching.